Okay, let's get started, everybody. Thank you all for coming. We're honored today to have as our colloquium speaker, Professor Frank van den Bosch. Frank is Professor of Astronomy at Yale, where he's been since 2010, having previously been professor in Salt Lake City, Utah, and previously to that, a group leader in Heidelberg, MPIA. Frank is an expert in all things cosmological. He has worked on the formation of large-scale structure, on stripping in galaxies. The recent work he's done on dynamical friction, I think, has been a big step forward in the analytical understanding of dynamical friction. Some of the best work that's been done in several decades on that problem. And he's also, of course, the co-author of the famous book, Mo, van den Bosch and White, on galactic evolution and formation. And he's going to tell us today about his new insights into cosmology and the galaxy halo connection from nonlinear scales. So, Frank van den Bosch.
Thank you for the invite and the introduction, and for letting me talk about some work I've been doing over the last sort of decades, and we focus on the latest work that was done by my previous student, Johannes Lange, who's currently at Michigan, and my current PhD student, Gustav Mitra, at Yale. So I'm going to start by saying a few words about the galaxy halo connection and about halo propagation modeling and why we care. I'm then going to apply it, using data. We're going to then try to use it to constrain cosmological parameters. And it's going to introduce a problem known as the S8 tension. Okay, and it comes from trying to fit clustering and lensing simultaneously. And I'm going to introduce the elephant in the room in this business, and it's assembly bias, briefly talk about that, and then introduce an alternative method to address this issue, which is satellite kinematics, very old technique, very little used. I'm going to talk about a new tool that we've developed called Basilisk that can analyze satellite kinematics. And I'm going to end by then applying clustering plus satellite kinematics in order to infer cosmological constraints to put this SH tension in new light. All right. So ever since basically the beginning of this millennium, I have been working on the galaxy halo connection. And broadly speaking, what I'm interested in is to constrain this conditional probability function. It says, given a halo with properties H, which is a set of halo properties like halo mass, spin parameter, shape, what is the probability that such a halo hosts a galaxy of properties G, such as luminosity, star formation rate, color, size, and unit? Now, why do I care about that? Well, first of all, that construct is the outcome of the complicated process called galaxy formation. It's galaxy formation which sets that. And in principle, what we try to do in galaxy formation is to start with initial conditions and run it forward on a supercomputer with hydrodynamic simulations and try to predict the outcome of this galaxy halo connection. But ultimately, in the end of the day, that's going to end up using some subgrid physics and some assumptions and some effective theory. And what we're trying to do is to go at it from an empirical direction. We're going to say, okay, given the distribution of galaxies and what we know about them, can we infer this galaxy halo connection? And if so, what does it tell us about galaxy formation? Okay. So it's a complementary approach in that respect. The galaxy halo connection also links what we can see, aka galaxies, to what governs the dynamics of the universe, which is largely dark matter. Okay. And whenever you use galaxies in order to try and constrain cosmologies, at some point or the other, this galaxy halo connection come into play. So how do you constrain it? Well, you start with an observational galaxy survey, ideally a redshift survey, and from that you can construct a number of different summary statistics. You can look at the clustering of the galaxies, for example, as a function of luminosity. You can look at gravitational lensing of background sources, okay? And that tells you something about the masses of the halos associated with these galaxies. And something similar can be done with satellite kinematics, where you use the motion of satellite galaxies to constrain the halo masses. So all these three, and there's other things like group catalogs, can be used to inform the galaxy halo connection, which then ties into galaxy formation and cosmology. And I talked about all the different galaxy and halo properties that you might want to consider. Now this field is moving slowly, okay? So it's been going for 2 decades. And most studies still today only use the galaxy properties luminosity, and the halo property is halo mass. So we're slowly moving beyond that, but that's what I'm going to focus on today as well. So my complicated conditional probability function becomes somewhat simpler. I'm going to ask, what is the probability that a halo of a given mass m hosts a galaxy of luminosity L? And rather than working with this probability function, we're going to work with what we call the conditional luminosity function, which is just a statistical construct that we introduced back in 2003 when we started working on this field. Now, what is the conditional luminosity function? Phi L given m. It basically describes the average number of galaxies of luminosity L that reside in a halo of mass m. So you can think of it as a luminosity function as a function of halo mass. And this conditional luminosity function is extremely powerful. For example, if I integrate it over halo mass, weighted by the halo mass function, it says how many halos do I have of mass m per co-moving volume. This then tells me how many galaxies of luminosity L does each of those halos host on average. If I integrate that over all halo masses, I get the average, the number density of galaxies of luminosity L per co-moving volume. That's an observable global galaxy luminosity function. This is the halo mass function, which we think we know for a given cosmology. And you see that the conditional luminosity function links those two things together. You can also integrate it over luminosity weighted by the luminosity of each galaxy. And it gives you the total amount of light that on average emanates from a halo of mass m. So it describes the average relation between light and mass in the universe. And finally, you can, from it, construct another very often used halo occupation statistic, the HOD, the halo occupation distribution. How many galaxies are there in a halo of mass m that are brighter than some minimum luminosity? You just get that by integrating conditional luminosity function. Now, I'm not going to describe in any detail the functional form that we use. We basically model this conditional luminosity function using some parameterized functional form, which is well motivated. Okay, we've been doing this for 20 years. The main thing to remember is we have in total about 12 free parameters that characterize this conditional luminosity function. That constitutes the model, and the aim of the game is to find and constrain those 12 parameters given some data. And one of the data sets that we can use is
per mass.
Those 12 parameters describe all the mass dependencies.
Okay.
There's about 5 or 6 parameters at a given mass, and then 12 parameters describe this mass dependencies. So one thing we can use is clustering. Okay, so how does this work? Well, you take a redshift survey like Sloan. Okay, we're in Princeton here, you've all seen this. Then from that, you can construct, for example, the projected correlation function as function of projected separation. Different colors correspond to different magnitude bins. Okay, red are the bright galaxies, blue are the faint galaxies. This is from the work by Edith Zahavi, a long time ago already. For those of you who don't know what a projected correlation function is, that's just taking the correlation function and integrated it along the line of sight. And the reason why we do that is then basically integrate out line of sight velocity redshift space distortions. Okay. The upshot is you can't really see that here because it was offset from each other for clarity. But if you measure something like the correlation length, which is basically defined as the radius of which a correlation function is unity, okay, just think of it as clustering strength. And you plot it as a function of magnitude. Okay, for the theorist, it's bright, faint, right? What you find, and what we have been finding, is that brighter galaxies are more strongly clustered. Okay, it's now very well established. Now, what about halos? Well, you can go to a numerical simulation, okay, identify halos of a given mass, and measure the correlation function of halos as function of their halo mass. And if you plot that as function of halo mass, this is sort of a measure for the clustering strength. Okay, formally it's the halo bias, which is defined as a relation between the halo-halo correlation function, okay, the clustering of halos of mass m, and the matter-matter correlation function. That's a correlation function between dark matter particles in a simulation. And on large scales, there's a linear bias relation, okay, and that bias has a dependence on mass. And basically, just again, think here, clustering strength. And what you see and what you can predict, and you can analytically calculate this for Gaussian random fields quite trivially, that more massive halos are more strongly clustered. Okay. A minute ago, I told you observationally, we know more luminous galaxies are more strongly clustered. And since galaxies live in halos, there's only one logical conclusion. More luminous galaxies reside in more massive halos. Okay. That's basically how this works. And in principle, we do this a little bit more sophisticated. We have something called the halo model. I made it very small. You're not supposed to read this. The main message is we are able to compute the full correlation function of halos of a given mass for a given cosmology. And so for given cosmology, I know what the halo mass function is. I can calculate what the halo bias function is, and from those two constructs, I can now compute via this recipe the halo-halo correlation function as function of halo mass. So pictorially, with this information, I know how many halos there are of a given mass and how they're clustered in space. And if I now combine this with a halo occupation model that says how many galaxies of luminosity L are there in each of these halos, I hope you can see that you can now compute trivially the same recipe, the galaxy-galaxy correlation function as function of luminosity. I've also shown you how you can compute from these two things the luminosity function, and those two are observables. Okay? And those two we can use now, and we have about 12 free parameters here with a Bayesian engine to try and constrain the posterior space of those 12 parameters. And then if you're brave, you can try to do this for different cosmologies and see if you can put some constraints on cosmological parameters. As I said, we started playing this game about 20 years ago. This is one of our first papers in 2004, where we applied it to the 2DF galaxy redshift survey. So this is the luminosity function, okay? And these are the correlation lengths as function of magnitude in blue, and in yellow, green, whatever it is. Those are the 68 and 95% confidence levels, intervals that we obtained from our fitting procedure. So now we have constrained these CLF parameters, and we can then make predictions of what is the average luminosity as function of halo mass of these galaxies. And you get sort of this broken power law relation. And around the same time, Phil and Ostreicher did something similar called abundance matching and obtained a very similar relation. And these were sort of the first results where people really started to get constraints on the galaxy halo connection over a large range of scales. You can also plot the mass to light ratio if you want. But fast forward now 10 years, 2013, this is from a nice review paper by Peter Baruzzi. What Peter is plotting here is the stellar mass to halo mass ratio, the function of halo mass. And these are all different constraints from different analysis of sort of this halo occupation modeling, using clustering, some are using lensing, some are using abundance matching. And the upshot is, look, within a factor of 2, they all agree very nicely. And this is astronomy, factor 2 agreement means perfect agreement. Mass, 10 to the 12, and you can see some sort of interesting trend here. At 10 to the 12, the stellar mass to halo mass ratio is the highest. That basically means that this is the halo mass scale at which, for whatever reasons, galaxy formation is apparently most efficient in forming stars. Now, how efficient? Well, not very efficient, because even at its maximum efficiency, the stellar mass is only about 3% of the halo mass. And we said, okay, let's assume cosmology, the best fit parameters from the first year data release of WMAP. And we got really tight constraints. Now we're plotting mass to light ratio, sort of the inverse of what I plotted on the previous plot, where I was plotting stellar mass to halo mass. Now I'm plotting halo mass to light. Okay, so now we have this thing here at 10 to the 12 being a minimum. We got this really tight constraint, super tight constraint. This was fitting Sloan data. But when we changed it to the best fit cosmological parameters from WMAP 3, we got equally tight constraints, but they were clearly offset. And now the most important part of this is both were fitting the clustering data equally well. Couldn't tell the difference. It kind of makes sense, right? If you change your cosmology, your halo bias function changes. Your halos are differently clustered. To fit the data, what I have to do is I have to put my galaxies in different halos. Okay? And therefore the mass to light ratio changes. But the constraints were extremely tight, but clearly dependent on cosmology. But I couldn't tell them apart based on the clustering. But if I now can somehow combine this with an independent constraint on the mass to light ratios, then I can break the degeneracy. So I have to find a way to measure halo masses around galaxies. Well, one way to do that is through galaxy-galaxy lensing. So here's a pictorial view of how that works. Suppose I have a bunch of background sources, and I take a foreground galaxy with a big halo and put it in front of it. It's going to cause tangential shear distortions of these background galaxies. Now, this is highly exaggerated. Okay? In reality, you can barely see this. It's a really, really tricky measurement, okay? But it can be done. And the strength of these shear distortions, okay, which we express in terms of something called the excess surface density, don't worry about it, it's just related to the galaxy dark matter cross correlation. Because what you're measuring is how much dark matter is associated with this galaxy. Okay? Because it's the dark matter that's doing the lensing. And with the conditional luminosity function, I've shown you how I can compute the halo-halo correlation function. I can compute the galaxy-galaxy correlation function. it is trivial, and I hope you can understand that it's also simple to compute now the galaxy dark matter cross correlation function. All you have to do is assume that halos have an NOW profile and you're done. So what we can then do is we have these two fits for WMAP1 and WMAP3 cosmology that fit the clustering equally well, and I have a CLF constraint for each of them. And for each of those, I can now compute the prediction for the excess surface density. Because I can work out this thing, I can predict what the lensing signal looks like. So here are those predictions. So this is this excess surface density or lensing shear, function of rejected separation from the foreground galaxy. These are faint galaxies, you go to brighter galaxies. This is data from Rachel Mendelbaum back in 2006. The red dots are the data. First thing to notice, if you go to brighter galaxies, the lensing shear gets stronger, okay? Once more telling you brighter galaxies have even more massive halos. And overplotted are the predictions for the WMAP3 and WMAP1 cosmologies. And I want to emphasize, these are not fits to the data here. These are predictions that we take from the fit to the clustering and we predict the lensing. And you can clearly see now that the WMAP3 prediction does much better than the WMAP1 prediction. So we got totally excited and we said, okay, let's now apply this full-fledged and put some constraints on cosmological parameters. And this is what we got. Okay. You can't see the inner contour. But there's omega matter, sigma H space, and these are the constraints that we obtained back in 2013. It took us actually 4 years to work this out. It's not as trivial as we thought it was going to be, but this was the result we had in 2013. And back then, if you compare that to then best fits on the cosmic microwave background, that was in perfect agreement. Okay, so we wrote that constraints are in good agreement with cosmological constraints. Then a few years later, Planck spoiled the party. He said, no, it's down here. And there's some tension here. And the tension sort of hasn't died away. For example, DES, year one, did an analysis called the 3 times 2 point correlation function analysis and obtained these constraints here. These constraints are larger or weaker than ours. That's because they throw away all the scales, all the data on nonlinear scales. They only looked at large linear scales. In 2019, and then Planck refined their constraints. And then in 2019, Johannes Lange analyzed clustering and lensing in the Bosch data and obtained these constraints. And basically, this sort of tension between the Planck results and these sort of clustering plus lensing results has become known as the S8 tension. And S8 is just a combination of sigma 8 and omega matter, and basically this is the direction of increasing S8. It was perpendicular to these sort of bananas that you often see. Now, we are not the only ones who've done this, by any means. Many people have done this over the years. Okay? This is just a subset. Alexis Leteau, 2017 analysis of Bosch CMS data. Here are the constraints, here is Planck. Okay, same thing. Cosmic shear analysis by Asghari et al. The KITS 1000 sample. Here is a result. I think Alex Ammon talked about this here in Princeton last November. She presented the cosmic shear analysis from DES year 3. Here is S8 now as a function of omega matter. These are the constraints. Here is Planck. Okay, so this S8 tension doesn't want to go away. This is a paper that we're about to publish. It sort of summarizes this. So this is S8 on the x-axis here. Here are the constraints from the cosmic microwave background in blue. And all these different studies consistently find S8 to be low. Now, by themselves, each of these individual measurements is not a 5 sigma, nail in the coffin, help, alarm kind of thing. But, it keeps, the problem is persistent, let's put it that way. This is also sometimes called the lensing is low problem. And the reason for that is if you pick the Planck cosmology and you now fit the clustering and then predict what the lensing should be, like what we did some time ago, you do it for the Planck cosmology, then your predictions for the lensing are high compared to the data. So the data, the lensing data is low. That's where this name comes from. Okay? This is from Alexis Leteu's work. This is again this shear. Okay, so here's a summary of all that. There's a persistent tension, and what is causing it? Well, I can think of 4 things. Systematic errors in Planck. I wouldn't dare to say that in front of an audience full of cosmologists. They start throwing things at me. I don't really think this is, I think Planck is pretty solid. There's a tension, of course, in Hubble parameters, or who knows. But maybe then what we're seeing is new physics beyond the 6-parameter lambda CDM vanilla cosmology. Maybe it's evidence for non-zero neutrino mass, which actually goes in the right direction. But before I write that Nature paper, I better rule out these alternatives. And one of these alternatives is, well, there might be something wrong with this lensing measurement. These are really, really tricky measurements. Okay? You're trying to measure these really small shear distortions in some data, point spread function issues, whatever. Now, a few years ago, I thought that was probably it. But now that all these different lensing analysis, all these different studies starts to look really robust. And it's probably getting more and more likely. Well, maybe then there's something wrong in the modeling. And this is indeed where there are some issues. And one of those that I want to briefly discuss here is assembly bias. So what is assembly bias? Assembly bias is the following. If you go to a numerical simulation and you pick halos, and you measure the correlation function of halos, I told you more massive halos are more strongly clustered. But if you now look at halos of a given mass, and you split them into halos that assembled early and that assembled late, okay? And this was first done in a very nice paper by Gao and Simon White. You make a plot of the young halos, the ones that assemble late, and old halos, the ones that assemble early. You can see by eye that they're clustered differently. Okay? And you can plot again this halo bias as function of mass. So this is for all halos. This is this mass trend I talked about. If you now split them in young and old, you see that at a given halo mass, there's a dramatic dependence of clustering on the assembly time of the halo. Now, this is important because all our halo occupation models do one thing. They're based on what we call the mass-only ansatz. We assume that the occupation statistics only depend on halo mass. But if they also depend on the assembly time of the halo, and why wouldn't they? Then you're making a big error, or you can potentially make a big error. Okay, and I'll give you an example of that. Anyway, this is, I also like to think this is the elephant in the room, because we've known about this since 2005, and the entire community sort of comes up with wishy-washy arguments. Why now assembly bias on the core? It's only in the last few years that people start taking it more seriously. And the reason why we're so reluctant to take it on is it's complicated, because it's not just assembly bias that sets a clustering strength. It's every freaking halo property you can think of seems to correlate with clustering strength, and it becomes an unsurmountable task. But here's the potential problem, right? So here's an empirical fact. Red galaxies are more strongly clustered than blue galaxies at a given luminosity. Okay? In the traditional halo model, this means only one thing. Red galaxies live in more massive halos than blue galaxies. But if you allow for assembly bias, you have an alternative explanation. No. These galaxies live in halos of the same mass, but the red galaxies live in the halos that assembled early, and the blue galaxies in the halos that assembled late. And that doesn't even sound so stupid, because if the halo assembles early, the galaxies probably formed early, and they're redder, therefore, than in the other case. So this is a degeneracy. You suddenly have a degeneracy of two solutions, and how do you break the degeneracy? Now, to show you what it can do, in 2016 with Andrew Heron, we started actually including some assembly bias into this framework. And we did this in a very simple way. We call this a decorated halo occupation distribution. So suppose we have a model that says, without assembly bias, on average, there's 2 galaxies per halo at a given mass scale. Now we introduce another parameter that we can tune up and down. And if we tune it up, we put all these galaxies, we keep the same number of galaxies per halo on average 2 galaxies per halo at that mass scale. But all of them sit in the older halos. So if you down all the way down, they all sit in the younger halos. So by adding one simple parameter that's orthogonal to the other stuff, we can introduce assembly bias and play with it. So what we then did is we went back to this analysis that Johannes did in the Bosch data, okay, where he fitted the clustering and the lensing. And what he does here, he fits the clustering and then he makes a prediction for the lensing. And he has a posterior from fitting to the clustering, and over that posterior, he makes these predictions. This is uncertainty in the lensing. Okay? So this is plotted so that the model sits at 1, and overplotted is the data. Okay? This is again, this lensing is low issue. So here sits the model, and this is the lensing is low problem. And there's a small uncertainty that comes from the posterior on the constraints to the clustering. And now all we do is we allow now for assembly bias, okay? And we do this in different ways. I don't want to go into the details. But if you allow that assembly bias, you have more freedom. Okay? You certainly have more ways in which you can fit the clustering. And that opens up your uncertainty. And the blue contours now show the uncertainties if we allow marginalized over assembly bias. And it goes in the right direction. It mainly goes in the direction that it predicts lower lensing signal. It's not sufficient, even for the most extreme assembly bias models that are allowed by the clustering. But at least it seems that it's important to take it into account, if anything else. So this then comes to the point, where are we going from here? In the next few years, years, yes.
Is there an expectation that the assembly bias is the largest correction? You said there's
there's other things, right? It might well be. I actually think it is, but there's another effect that people often bring up, which is baryonic effects. Baryonic effects can change the halo masses and halo density profiles, and I think that plays a role on very small scales. But on the somewhat intermediate and larger scales, assembly bias is clearly dominant over those effects. So I said in a few years, we're going to have things like Euclid and Deci. It's going to way more galaxies. And the question really is how to optimize scientific return from these really $1 billion+ investments. And there's different approaches going on. A large fraction of the community that works in this field is going to say, well, you know what, these nonlinear scales, this is really hard with all these nasty effects. We're going to ignore it. And many studies still do that to this day. They throw away all the data on scales less than a few megapascals. Now, to me, that's not optimizing the scientific return from these investments. Okay? Well, the alternative is, okay, you just have to bite the bullet, develop models for assembly bias, and marginalize over it. Okay? But the problem is, how are you going to ever convince the community that you are complete? There's many ways in which this assembly bias can come about. And that really is the problem, and why people are very reluctant to go in that direction. I'm going to advocate an alternative method, is to say, add more different kinds of data that allow you to break the degeneracies between these things. And one way to do that is through satellite kinematics. Okay? So this is just using the motion of satellite galaxies as they zoom through the halo around the central, and that also allows you to measure halo mass. Now, interestingly, this is independent of halo assembly bias, simply because it doesn't depend on the clustering strength of the halo. You just look at an individual halo and its potential. Well, I don't care how it's clustered. So that's a good thing. Even better, I don't need any additional data. You give me a redshift survey, I'm done. I don't have to go out and measure tiny image distortions in a photometric survey or any of that. It comes for free. Yet, this has been severely underutilized to date. I only know of 2 studies that have used satellite kinematics to really constrain the full galaxy halo connection. And incidentally, those were both run by me and my students. 2009, I burned Stuart Moore on that project, and in 2018, I burned Johannes Lange on a project like that. Now, why is it that this is underutilized? And I think many people in the community think, well, you can't model this sufficiently accurately. Typically, when you model satellite kinematics, you make a genes assumption of genes equations, but these satellite galaxies are infalling populations, and they're not realized, they're just sloshing around. And by the way, how do you know that it's a satellite and a central, I'm going to convince you in the next 10 minutes that this is not an issue. Okay? You can really do this extremely accurately. So indeed, how do you then find centrals and satellites? They don't come labeled as such. Okay? So the way this is done, and the way everyone does it, basically is you put a cylinder around each galaxy, okay, and you ask, am I the brightest galaxy in my cylinder? Okay? This is a cylinder in redshift space and a certain opening angle. And if you're the brightest galaxy in your cylinder, you're called a primary. And the idea being, hopefully you're a central. And then you put potentially another cylinder around it, and you say all the fainter galaxies in that cylinder around this primary, I'll call them secondaries, ID being, hopefully they are satellites. And what you can do is you can play with these criteria of how big your cylinders are to try and optimize this so that you have large purity and large completeness. Now, what you then do is you have your primary secondary, and each primary secondary pair, you measure the velocity difference along the line of sight from your spectra. And you plot that velocity difference as a function of the luminosity of the central. And if you do that, you get a nice trumpet shape plot like this. And what you see is that if you go to brighter primaries, the satellites are moving faster on average. Once again, it's just showing you immediately brighter galaxies leaving more massive halos. Right? So the way, you can also see interlopers here. These are probably galaxies that I've selected as a secondary that live in my cylinder, but they're clearly not related to the primary. But they're not that hard to correct for. So what you then do is you then take a slice, you say, okay, let's bin all the centrals in a given bin here, and plot the velocity distribution, P delta V, of all these satellites. So you stack. And then you measure this velocity dispersion, this is the satellite velocity dispersion, and you can now plot that as a function of the luminosity of the central, and your summary statistic is here. And now all that you need to do is to turn this velocity dispersion here into some measure of halo mass, and that is typically done using some virial theorem or Jeans equation, something very simple. I already said. No, this method, incidentally, goes back to 1933, at least. Okay, when Fritz Zwicky applied this to the coma cluster and famously found that there was dunkle materie, right, dark matter, just by using the velocity motions, the motions of these satellite galaxies in coma and applying the virial theorem. Now we have to move forward by about 60 years for our next serious attempt on this, and this is Dennis Zuritsky's thesis. Okay, in 1993, they had 70 satellites around only about 50 isolated spirals. This is the data, delta velocities function projected radius. And Zuritsky used this to sort of show, look, on average, these spiral galaxies have massive halos around them of about a few 10 to the 12 solar masses. Okay. This was sort of the state of the field in 1993. Fast forward another, 16 years. This was a thesis by Surat Moore, working with me in Heidelberg. And we wrote a whole bunch of papers on satellite kinematics, applying it to Sloan data. We had about 6,000 satellites, around 3,000 host galaxies. And here's the result of this entire analysis. This is plotting as a function of the luminosity of the central, as a function of the stellar mass of the central, or primary, I use those terms, distinction, plotting the inferred halo mass from the satellite kinematic. And let's look at this plot here in black. This is for all galaxies. And you see, okay, more massive galaxies leaving more massive halos, no surprise there. But then we were able to split it in red centrals and blue centrals. And what we found is that at a given stellar mass, the red centrals live in more massive halos than the blue centrals. And remember, I talked about this, that the red centrals were more strongly clustered, and one option was halo mass, and the other option was assembly time. Well, this breaks the degeneracy. This shows that actually it most likely it is halo mass after all. So this is how satellite kinematics can help you to break these kind of degeneracies that come from clustering and other methods. All right. So now the question comes, can we do better than this satellite kinematic analysis I just showed you? I wouldn't ask the question if it wasn't yes. And yes means with Basilisk. Yes.
Quick question. Are you sensitive to the kinematics of the different galaxies, the kinematics of the satellite populations, depending on when the halo assemble? Namely, how tangential the orbits are, how radial the orbits are.
So this method can actually probe the anisotropy. Okay, so we can constrain it simultaneously with halo mass, so we can break the mass and anisotropy degeneracy. The previous method that I just showed you, not, because there we only use velocity dispersion. We're going to move now to a method that uses the full PDF. Now, Basilisk is a perfectly legitimate acronym. For satellite kinematics. And it's basically satellite kinematics with steroids, and it makes a number of important improvements. So for reasons that I don't want to go into, all the previous analysis with this stacking, what they need to do is they can only basically use volume limited samples. It means you go to a beautiful survey like Sloan, so you have redshift, luminosity, this is the flux limit, you have all these galaxies there, and you make a cut like this, and you say, we're only going to use these galaxies. So even with something like Sloan, we ended up with only 6,000 satellites. But with Basilisk, we can use a full flux limited sample, and we get a bewildering 43,000 satellites. Okay, so the amount of data that you can use goes up dramatically. Most importantly, though, what we do differently is that the standard method stacks galaxies and then uses this summary statistic, sigma sat as a function of luminosity. So from the entire data, you end up with 10 data points. And basically, you're only using the velocity dispersion of your PDF, what we talked about earlier. Plus, you require binning, and binning is sinning, and why would you do it? So what Basilisk does, it doesn't make use of any summary statistic. It just uses the data in its raw form. And what is that raw form? It says for each central, I have basically a set of data for all of the secondaries. For each secondary, I have a measure of the velocity difference along the line of sight and a measure of the projected separation. And I'm just going to ask, given a model for the conditional luminosity function, what is the probability that I get that data? What is the likelihood? I'm going to maximize my likelihood. Okay. That's how it works. Finally, when you actually put these cylinders around your galaxies and you find your primaries, for every primary that you find that has at least one secondary and that you can use for your satellite kinematics, there's about 9 primaries that have 0 secondaries in the cylinder. And so you don't have any data for the velocity dispersion or anything, you don't use it. But if you actually plot the probability that my secondary, or my primary, sorry, has 0 secondaries, okay, and plot as a function of luminosity and different redshifts, there's a lot of information there. This tells me information about how many satellite galaxies on average a central has. And that can be used to constrain the conditional luminosity function. So Basilisk uses this data in tandem with the actual kinematics. So how does it work? Well, it is a Bayesian hierarchical approach. I don't want to go through the details. I want to just highlight this thing. This is basically what we grind on a billion times. Is that given a model, theta, that's this 12 parameters of my conditional luminosity function, what is the likelihood of the data? And for that, I say, well, I don't know for a given central, at a given redshift, I don't know what halo mass it lives. So I have to marginalize over all possible halo masses. Okay. And once I know what its halo mass is, I can now calculate using a genes model, right? So I can calculate what is the probability that I have this velocity and this projected separation. And this here, this is where your conditional luminosity function goes in. If you have your conditional luminosity function, you can compute this probability, which we do, and then we can integrate it over halo mass. So the halo masses now become the latent variables in this hierarchical approach. And you just grind this through the data. Now, as I said earlier, we're using a spherical genes model, although we allow for anisotropy in the genes model. But, do satellite galaxies really obey the genes criterion? We don't know, so we have to test this. And we test this using a mock data set. So we start by taking a very large cosmological volume, simulation, and body only. This is the SMDPL simulation, those of you who are familiar with it, for the Planck cosmology. We populate the halos with galaxies according to a conditional luminosity function model. And we position the satellites on the subhalos. And the satellites therefore get the positions and the velocities of the subhalos. So we're not assuming that the satellites obey the genes criterion. They only obey the genes criterion to the extent that subhalos do. Then we construct a mock survey by putting a random observer somewhere in that box. And we let her make a survey. And we take everything we can think of into account: the Sloan footprint, fiber collisions. For those of you who know what that is, it's really nasty stuff. Redshift space distortions. And we make basically a mock redshift survey. And then we have a mock redshift survey, and we run our cylinders over it to find primaries and secondaries. The nice thing in the mock is we know which of my primaries are actually centrals and which of my secondaries are actually set lines. So one thing you can first do is actually ask, how well does this primary secondary selection really work? It turns out that we have an impurity fraction, which means those are the primaries that actually are not centrals, okay, that actually happen to be set lines. That fraction is less than 5%. And this is, partially tuned because that's how we tuned our cylinders to get the impurity fraction down. And what we can do with the mock is we can analyze the data with the impurities in there and with the impurities taken out, and we find that it makes no difference. The inference of the conditional luminosity function is basically indistinguishable. That's a big few because that could have really screwed things up. We can also measure the interloper fraction. Now, those are secondaries that actually are not satellites in the same halo as the central. Now, those actually can be really large. You can have 80%. Okay, this is the luminosity of the primary, and this is the interloper fraction, and it goes up to about 80% at the low luminosity end. But it's not a big deal because most of those interlopers sit in these high velocity tails. Okay, so this is the PDF, and in black are the true satellites, and in red are the interlopers. So most of them sit in this extended envelope. That's easy to correct for. But you also see that there's a bunch that actually bump up here, right where the halo is. Interlopers. Well, these are interlopers, but why is that? Well, partially that's simply because interlopers are a real background that have completely nothing to do with the halo, but they're also an infalling population. Okay? And anything that's infalling due to the Kaiser effect is going to crowd around delta V of 0. Now, that's not necessarily a bad thing because although you may get a contribution from those, they do tell you about the halo mass in the same way that satellites do. And you also have a backsplash population. For those of you who know what these are, these are satellites that are really actually satellites, but they just live outside of the very radius. So I don't have time to go into the detail. What we do is, this interloper model actually is really more tricky than I thought it would be. We don't want to just assume a constant, which is what everyone in the past has done. Our functional form actually looks like this. Okay, partially what is slightly inclined is because you actually have a cone. Okay, and it means you have more galaxies in the background interlopers than in the foreground. So that's why you get this sort of inclination. And then we have this contribution from infall and backsplash, which we model. We basically don't model it. We measure it in the data by measuring the distribution of velocities of galaxies in a shell around the cylinder. And then the only thing that we have to control after that is the normalization. How many interlopers are there? And that we model, and that's we marginalize. You can ask me questions later. I want to move on by showing you the test on the model. And again, there's too many panels here. Focus on this one. It's the luminosity of the central as function of halo mass. The red dots are the input conditional luminosity function. Okay? So that's how I populated my M-body simulation with galaxies. I'm not sure you can see it, but there's a very thin blue line here. Okay, that is the 68% constraint that we get from Basilisk running it over this data. And it's wickedly accurate and precise. And here's, for example, the scatter in the galaxy halo mass connection. Okay, what is a scatter at a given halo mass? What is a scatter in the luminosities of centrals that live in those halos? Well, we put in 0.15 dex, and we recovered it very nicely. Here are the actual interlopers, the true interlopers in the mock, and the curves that go through it are the models. Okay, we marginalize over that, and we basically recover. We can actually find interlopers very accurate. We even get the anisotropy right. So this is the velocity anisotropy that we infer. We're plotting here only this beta parameter from 0 to 0.3. We find an anisotropy of about 0.15. Now remember, we put the satellite galaxies on the subhalos. So what we can do is we can go into the M-body simulation and measure the anisotropy parameter of subhalos in the halos, and that sort of covers this range between these dashed lines. And it's almost too good to be true. It really works. All right, are you all convinced? Let's go and apply it to Sloan. Here's the actual data. Beautiful trumpet shape, many satellites. You can see individual clusters stick out. Okay, this is the projected separations. Here's this probability that you have 0. Secondaries is function of luminosity, and all this data goes into Basilisk, and we grind and grind. And here are the results. This is for the Planck cosmology, the constraints that we get on the luminosity as function of halo mass. And again, the blue thing that you can't see, but we follow the green dot. Those are constraints that we get. They're extremely precise. They're in good agreement with previous analysis from a variety of different techniques. Okay? Except that our constraints are significantly tighter. The interloper fractions that we infer, they look very similar to what we had in the mock, which is a good thing. The scatter that we constrain is about 0.18 dex. Okay, there's a weak hint for a mass dependence, but not much. There's some inconsistency with previous results that I don't want to go into, but I'm happy to answer questions about that. Anisotropy, we find the anisotropy in the Sloan data to be 0.1, which is amazingly similar to what we find for subhalos. Okay, so it really seems to work. And now we get to the final result. All right. Oh, before we get to the final result, this just, okay, you claim that you find some constraints, but how accurately are you actually fitting the data? Well, I'm not, binning data or anything when I do the analysis, but for this, I'm actually binning data. So what I do is I take bins of luminosity and redshift in this way, and for each bin in luminosity and redshift, I now, in the data, look at what is a PDV of the velocity difference between the sentinel and satellite, and I'm pulling the log of that so you can see the tails very nicely. And then I use the model to predict what it should be. And you can see, okay, this is not what we're actually fitting. We're fitting the data in a raw form. You can see that we really nicely and accurately fit the data. You can see here the slope that I was talking about. You can see that really in the data, it's there. We also can do this same thing for the probability that I have n secondaries as function of luminosity and redshift. Okay, this is again n secondaries 0, 1, 2, all the way to 20. Red dots are the data. Blue lines are the model predictions. So in an absolute sense, we're really fitting this data very, very, very nice. All right, so now let's go to cosmology. So we thought this was going to be easy 5 years ago when I thought that. So we've been working very hard on this. It's actually tedious to do because it takes a lot of CPU time. So what we do is for a given omega matter sigma 8, we can do this entire analysis. Okay, and then we can compare different cosmologies. And the first thing we need to do is do this on the mock. Convince ourselves that we can recover the input cosmology. So that we just finished a few weeks ago. So here's the input cosmology, Planck, based Planck-like. Okay, it's not perfectly Planck, but here are the constraints that we get if we run Basilisk over clustering plus satellite kinematics. Okay, and we're perfectly consistent with the input cosmology, and that's what we get. So now that we have convinced ourselves that this should yield unbiased constraints, let's apply it to Sloan. Unfortunately, it's still running, but we were smart enough to, before we do the full grid, we decided let's run a one-dimensional analysis where we just vary it along the direction of changing S8. So here's a Planck cosmology, and we run a bunch of cosmologies, actually a bunch more than what is shown here, in this direction. Okay? And for each of those, we do the analysis. So that I can show you. So this is S8. Here is a Planck constraint and a 1 and 2 sigma constraint from Planck. Here's the results that we had in 2013 and 2019 from lensing plus clustering. And here is our results from satellite kinematics plus clustering. And I don't know whether I should be happy or sad. Yeah, it's consistent with Planck. Yeah, it's consistent with that. Yeah, it's in the middle. There is tension. There's no tension. I don't know. Interestingly, right at the same time, we're finishing a paper. Johannes Lange is leading that, where we reanalyzed once again the Bosch data, but now using better lensing data from KIT and from DES. And he is using the same machinery as before, including assembly bias. And this paper should come out in this week on the archive. And what he finds, and again, be sad or not, is perfect agreement. So where does this leave us? I would summarize it as follows. So here, this is that poll I showed before. We can now add another technique, namely satellite kinematics, and it just sits about here. All I can conclude is that there's no obvious issue with the lensing. It's not that suddenly if you remove lensing from this analysis and replace it with something, it completely changes. I guess that's good news for the lensing. The S8 tension persists. At least it's on the same end, but it's not significant. So maybe it's weakening. I don't know. You read in it what you want to read. All right. So future work. One thing we need to do once we're done with running that entire grid is complicate things for ourselves and say, okay, the conditional velocity function might not just depend on halo mass, it might also depend on concentration. And although we don't have assembly bias issues, and that it has nothing to do with the bias, concentration does affect the satellite kinematics. Right? It affects the potential well, and therefore affects the satellite kinematics. And I do expect that the occupation statistics depends on concentration for a very simple reason. We know that a halo that is highly concentrated assembles early. And those have today less substructure. This is well established in the literature. Okay? So high concentration halos have less substructure than low concentration halos, and therefore the number of satellites might be modulated with concentration. And that could actually be a very important effect. So we need to do this before we, claim neutrino mass detection or something like that. We can use Basilisk. It's extremely powerful to go and do things like work out the occupation statistics as function of luminosity and size, or luminosity and color. You can get a richer characterization of the galaxy halo connection. We can do a meta-analysis where we fold in lensing and see what happens. Ultimately, we're going to apply this to DESI. It's 10 times the data as Sloan, so everything is going to take 10 times as long. And you can play fun games like think about constraining gravitational slip using a combination of satellite kinematics and lensing. Although I think no one believes anymore that there's something wrong with GR or skills of a few hundred kiloparsec, but it's consistency check if anything. All right. So to summarize, halo occupation modeling is a powerful method to marginalize over uncertain galaxy information physics. That's one way to think about this, and thus constrain cosmological parameters. The combination of clustering and lensing consistently reveals this SA tension. Assembly bias and baryonic effects make it difficult to make reliable predictions for this. Okay, you marginalize over all this, and we don't know really what happens. Satellite kinematics, I hope I've convinced you, is an alternative probe that can yield precise and unbiased constraints. It's less susceptible to halo assembly bias, and it's easy to measure. You don't have to do anything. And so far, maybe there's a reduced SA tension on the horizon. Thank you.
Yes, well, having done this exercise with the satellites, going back, having done this Basilisk exercise, have you gone back to look at the actual stellar kinematics of those galaxies? And in the end, you learn more from the satellites than you would have learned from just the velocity dispersions or rotation curves of those galaxies.
Right, we haven't done it, but I've been trying to convince Marla, GR, who works on this kind of stuff, who has the kinematics of dwarf galaxies in the Milky Way, to actually run Basilisk and do that kind of analysis, because you use a full PDF analysis, shape data in your analysis. So it's very good for breaking the mass anisotropic judges. Is that what you're asking about?
No, there's just a tendency for galaxies in larger halos to have larger stellar velocities, higher rotation curves, larger dispersions, and you might worry about all sorts of, the self-gravity of baryons and so forth, biasing that. But now that you've done this with satellites, you go back and look at stellar kinematics. Were there those important biases or not?
My gut feeling would be exactly what you said. That is probing things on such small scales. Now you're really probing it on scales of 2-3 kiloparsecs, the velocity dispersion of a central galaxy. So to sort of link that to the halo mass in which a galaxy lives, I think baryonic effects are clearly extremely important. So I would not believe that that's a good accurate probe of the halo mass.
A priori, you wouldn't, but a posteriori.
A posteriori, now we can go back and plot these things and see how it correlates. Yes, that would be an interesting idea.
Thanks very much. Very beautiful result. Let me ask you the following. When you compare Planck with the others, there is, of course, the famous difference in the Hubble constant. I assume you are keeping the different Hubble constant for Planck and for the others. So that will cause a difference between the results. How much, if you change the Planck Hubble constant to be the same as for the others, how much of that will change? Because the Hubble constant enters into all of this cosmological analysis. So if you keep the same Hubble constant, how much will that change the results?
So I don't know what you mean by keeping the same, because how
much of this effect could be due to the different Hubble constant that Planck is?
We're not assuming any Hubble constant in the clustering or lensing or satellite kinematics.
But the Hubble constant enters into the cosmology.
So we have fixed the Hubble constant for the Planck level.
Right.
So I mean, if you're asking what happens if we set it to 72 instead of
If
68.
you keep all the other parameters, I'm trying to understand how much of this result really tells us about sigma A, omega matter, sigma A, or how much does it depend on the other parameters which you are not keeping the same?
I know you're asking. I mean, I have not done any of this. I have not tried this. We at some point, a long time ago, David, I think other people have tried to do this kind of analysis to see whether these S8 problem and the Hubble tension are related, and have not found a good relation between those two. That's my reading of the literature. But I have tried this myself.
Can you, I guess approximately, if Planck's Hubble constant, if you change it to the higher value of the Hubble constant, which direction will it change the sigma A?
Thanks, Ron. So we know, and you've actually shown that the satellite population that we see is only a subset of the satellites that have fallen in, right? Many satellites are tidally destroyed and we no longer see them. So how much could it affect your results if we're looking at a biased sample of survivors where, you know, the objects that survive may depend on many other properties of the halo, such as you alluded to, like concentration or assembly history or baryonic processes that determine the formation of the baryonic structure in the galaxy, in the halo.
So I think the answer is it shouldn't depend at all. I have a tracer population of some things, and if some process removes a bunch of them, maybe the ones that are on more radial orbits, because they get more easily disrupted, then I just end up with a tracer population that's more tangentially anisotropic, and my method should recover. It should see that it's tangentially anisotropic. Find it to be slightly radial anisotropic.
What if that depends on halo concentration or assembly history, or
Right.
whether there's an elliptical or a spiral? Yeah.
So I think we'll get some insight into these questions once we start concluding the concentration. Because I think that's going to be the dominant first order thing that's really going to matter, because we know that the number of satellites is modulated by concentration and the kinematics are modulated. But that's a good question.
Okay, we're past the hour, so let's carry on the conversation at lunch. Thanks, Frank. Yeah.